All right, let's dive right in. Multi-GPU and multi-node training. It's like giving your AI and high-performance computing projects that extra boost.
Yeah, like strapping a rocket to them.
Exactly. And we got some great stuff to work with today. A presentation from the Ministry of Electronics and Information Technology, NPSF User Workshop 2023, and a user guide on job scheduling and profiling.
Really practical stuff.
Yeah, by the end of this deep dive, you'll really get how these techniques are changing things, like in AI and scientific research, right?
Absolutely. It's amazing how they're making high-performance computing accessible to, well, everyone. Researchers, developers, they can tackle problems that used to require these massive supercomputers.
Totally. And we're going to break it all down. We'll be looking at tools like NVIDIA, NGC, and SLURM.
The unsung heroes, really, quietly powering some incredible advancements.
For sure. Okay, so NVIDIA NGC, it's kind of like this treasure trove, right?
Yeah.
Pre-trained models, SDKs, containers,
Mhm.
all optimized for NVIDIA GPUs.
It's like a toolbox full of these pre-built AI components. You can just assemble them and create your own solutions.
Saves you a ton of time and effort. No need to start from scratch. That's pretty cool.
And the NGC containers, those are really something. They have everything you need to run those complex AI workloads, libraries, frameworks like TensorFlow and PyTorch, even code examples, all pre-configured and ready to go. It's not just about simplicity either. It's about consistency in performance and security. NVIDIA's really rigorously tested and optimized these things.
Right, makes sense. So you're basically getting a pre-assembled computer instead of having to build one yourself. Just plug it in and go.
Yeah.
But I'm wondering, how easy is it to use these containers? It sounds a bit, well, complicated.
Actually, it's surprisingly straightforward. Let's say you want to use a TensorFlow container. You just pull the image from the NGC catalog, you use the docker pull command, then you run it with Docker run. You just specify any configurations you need.
So just a few commands, huh? That's impressive.
Exactly. NGC takes away a lot of that complexity. It lets you focus on what really matters, developing and deploying your solutions.
Right. Now, things get a little trickier when we scale up to multi-node resources. It's kind of like going from playing a solo instrument to conducting a whole orchestra.
Yeah, you need a way to manage all those parts, make sure they're working together.
Harmony. Right.
Lisa.
That's where SLURM comes in.
Exactly. SLURM. It's a powerful job scheduler. It's great at orchestrating resources across those multiple nodes. Think of it like a dedicated manager for your compute cluster. SLURM, it assigns tasks, makes sure resources are used efficiently, keeps everything running smoothly. Essential if you're working with large computations.
So it's the conductor of our compute orchestra, keeping everything in sync.
Perfect analogy. And to really understand how SLURM fits in, think about the software stack.
Yeah.
You have your login nodes, where users access the cluster, then management nodes, they handle administration, and finally, the compute nodes. That's where the real work happens, the number crunching.
Right. And SLURM makes sure all of that works together. So you can scale your workloads, use your hardware effectively.
Exactly. A seamless operation.
Okay, so SLURM handles that resource management. But let's talk containers. Everyone knows Docker, right? It's like the big name in containerization.
Yeah.
But I hear it can have some downsides, especially in high-performance computing.
You're right. Docker's popular, but it does have limitations with security and administration in HPC. For example, it relies on root privileges for managing containers.
Ah, so if one container gets compromised, an attacker could get into the whole system. That's risky, especially when you're dealing with sensitive data.
Precisely. That's where NVIDIA Enroot comes in. It's a solid alternative. Enroot creates unprivileged sandboxes, meaning containers run without root privileges. Much more secure, drastically reduces the risk of compromise.
Makes sense, like giving each container its own little secure playground.
Exactly. And security is not the only advantage. Enroot's also very user-friendly, straightforward design, easy to manage. And here's a bonus, it's compatible with existing Docker images.
So you can switch without rebuilding everything. That's a smooth transition. But what about actually using Enroot? Is it difficult?
Not at all. Enroot has a set of clear commands for managing those containers. For instance, Enroot import to import an image. Enroot create a container. Enroot start to start it up. And Enroot remove to, you guessed it, remove it. Pretty straightforward.
So Enroot, secure, user-friendly, and it works with Docker. Sounds like a winning combo. But now we have SLURM for the cluster and Enroot for containers. How do we make them work together?
That's where Pixis comes in. It acts as a bridge between SLURM and Enroot, allowing them to talk to each other, to cooperate.
So it's like the translator, making sure everyone understands each other.
Precisely. With PikeSys, you can launch those containerized tasks using those familiar SLURM commands, just like any other job. You're managing both the cluster and the container environment all in one place. And here's a key point. PikeSys is designed to handle those multi-node MPI jobs, essential for those computationally intensive tasks, the ones that need the power of multiple nodes.
That's really neat. It's like having a single control panel for your whole high-performance computing setup. But let's get practical here. How do you actually run a job with SLURM?
When you submit a job to SLURM, you use a job script. It specifies the resources you need, the commands to execute.
Like a set of instructions, right? Telling SLURM how to use the resources and what to run. Can you give us some examples of what these scripts look like, what parameters they use?
Of course. One key parameter is nodes. That tells SLURM how many compute nodes your job needs. Say you're working on a complex simulation that needs 4 nodes. You'd set nodes to 4, then you have n tasks. That defines the total number of tasks to distribute across those nodes.
So it's about dividing the work, spreading it across the resources.
Yes, and that's where you see the power of parallel computing. Breaking down your workload into smaller tasks, you can use those multiple nodes and get things done faster.
And what about the GPUs? How do we ensure our job can access them?
The gress parameter. You can request specific resources, like those powerful A100 SXM4 GPUs. It's like saying, hey, SLURM, I need these GPUs for my data crunching.
So we're giving SRM the info it needs to use resources efficiently. But it's not just about getting the resources, it's about using them well.
Yeah.
How do we make sure our code really utilizes all that parallel processing power?
Tools like TorchRun. They're made for distributed deep learning training, letting you spread the workload across multiple nodes and GPUs. Inside your SLURM job script, you can use variables like nodes to say how many nodes you're using, and proper node to control how many processes run on each node.
So TorchRun is directing the flow of data and computations, like a traffic cop.
Exactly. And what's great about these scripts is their flexibility. You can easily change the parameters, scale your computations for different problem sizes, different hardware setups.
Like building blocks, rearranging them for different computational structures depending on the task.
Exactly. SLURM and tools like TorchRun give you this powerful framework, really adaptable for multi-node and multi-GPU computing, all about optimizing for performance.
Okay, we've talked about setting up the environment, running jobs. But once it's all going, how do we ensure our code is performing at its best? We put all this work into the hardware and software. We want to get the most out of it.
That's a great point. And that's where GPU profiling comes in. It's like having a coach for your code, helping you identify areas to improve, optimize that performance.
Okay, I'm all for a code coach. But seriously, what does GPU profiling involve?
It's about understanding how your code interacts with the hardware, finding those bottlenecks that might be slowing you down. Those parts where your code is struggling to keep up with the GPU's capabilities. And then we figure out how to streamline those processes.
So it's like finding the kinks in a runner's form, those things that are preventing them from reaching their full speed.
Exactly. And it's not always just about raw speed. Profiling can help you optimize memory usage, throughput, making sure your application is running as efficiently as possible. No wasted resources.
That makes sense.
Yeah.
Before we get into the specifics, are there any common mistakes people make with profiling? Things to avoid?
Oh, definitely. One big one is trying to profile before your code even works correctly. It's like fine-tuning a car engine before the car is even assembled. Make sure your code is working right, producing the results you need, before worrying about performance.
Right. Easy to get ahead of ourselves, get caught up in optimization, and forget the basics.
Exactly. And once you have working code, remember that profiling isn't always just about speed. Sometimes memory efficiency or cost might be more important. The best strategy depends on your application, your goals.
So it's not a one-size-fits-all approach. We need to tailor our profiling to our specific needs.
Exactly. And to help you, NVIDIA has these great tools, Nsight Systems and Nsight Compute. They're like X-ray vision for your code. You see how it's interacting with the GPU, where those performance bottlenecks are hiding.
Those sound incredibly useful. Let's start with Nsight Systems. What's so special about it?
Nsight Systems gives you this comprehensive system-wide view of performance. It's like a bird's eye view of your whole application. You see how all the parts fit together, where those bottlenecks are.
Like a map of your code's performance, highlighting the areas that are slowing things down.
Perfect analogy, and one of the best features is the timeline visualization. It shows a detailed timeline of CPU and GPU activity, so you can actually see where your code is spending its time.
Wow, so it's like watching a movie of your code's execution. You can pause it, rewind, zoom in, really analyze it.
That's exactly it. And if you want to go even deeper, Nsight Systems has an event table and an analysis summary. They give you in-depth info on the system's behavior, like CPU utilization, process activity, GPU kernel execution.
It's like a team of detectives investigating every detail of your code's performance.
Exactly. And to help you focus on specific code sections, you can use NVTX annotations. They're like flags in your code, marking areas of interest on that Nsight Systems timeline.
So you can highlight the critical sections, make it easier to spot potential problems.
Precisely. NVTX annotations add context, They give meaning to the data, make it easier to see the bigger picture.
This is really useful information. Nsight Systems sounds incredibly powerful for understanding and optimizing code. But what about those CUDA kernels we've mentioned? Where does Nsight Compute come in?
Nsight Compute is the specialist. It analyzes the performance of those CUDA kernels. They're the core of GPU-accelerated computations. If you really want to understand how your code is interacting with the GPU at that low level, Nsight Compute is your tool.
So we're looking under the hood at the individual components of the engine, but can you explain a bit more about what CUDA kernels actually are?
Sure. CUDA kernels are functions that run on the GPU. They're written in CUDA-C, which is like C++, with added features for controlling the GPU's parallel processing.
So they're the instructions telling the GPU what to do, specifically designed to use all that parallel power.
Exactly. And Nsight Compute gives you so much detail about how those kernels are performing. You get all these metrics: execution time, memory accesses, instruction throughput. The works.
Wow, so it's like a microscope letting us see the inner workings of those kernels.
Great analogy. And to make sense of all that data, Nsight Compute has these visualization tools, like the roofline analysis. Helps you assess the efficiency of the kernels, guides your optimization strategy.
The roofline analysis. That sounds interesting. How does that work?
Think of it as a visual representation. It shows the theoretical performance limits of your GPU and how close your kernels are to reaching those limits. It shows you where the bottlenecks are, whether it's memory bandwidth, compute capacity, or something else.
Like a benchmark, then.
Yeah.
You can see how much room for improvement there is.
Exactly. And to make it even easier, Nsight Compute lets you compare kernel performance across different runs, so you can see how changes to your code are impacting things.
That sounds incredibly helpful. Experiment with different optimizations and see the impact right away.
Precisely. Nsight Compute gives you the tools to fine-tune those CUDA kernels. Get every bit of performance out of your GPU.
Wow, this has been a fascinating deep dive into multi-GPU and multi-node training so far. We've covered a lot. Containers, orchestration, those powerful profiling tools.
We've seen how to use NVIDIA NGC, how to manage resources with SLURM, and how to get a detailed look at our code's performance with Nsight Systems and Nsight Compute.
But there's more to come. In the next part, we'll keep exploring those profiling techniques. We'll get into even more specific optimization strategies to take your deep learning workflows to the next level. Stay with us.
Welcome back. Let's jump right back into those code optimization techniques for multi-GPU and multi-node training.
Last time we were talking about those little tweaks that can make a big difference, right? Like using the right kernel size or aligning filter counts. It's pretty amazing how much impact those small details can have.
Oh, absolutely. Especially in deep learning, with those large models, every bit of optimization counts. Even a small improvement can save hours, even days, in training time.
So where do we go from here? What other areas can we optimize to get that extra edge?
One area that often needs attention is the input data pipeline. It's like the fuel supply chain, If it's not running smoothly, your whole training process can slow down.
I like that analogy. So what kind of bottlenecks might we run into with the data pipeline, and how do we deal with them?
Well, one common mistake is loading data directly from disk to the GPU memory. You might think, get it to the GPU as fast as possible, right? But that can actually create a bottleneck, especially if you have a fast GPU but a slower storage system.
So it's like having a super fast sports car stuck in traffic, all that potential speed, but it can't go anywhere.
Exactly. A better approach is a staged pipeline. Load the data from disk to the CPU memory first, do any pre-processing on the CPU, then transfer that pre-processed data to the GPU in batches.
Okay, so it's like setting up an assembly line. Each stage is optimized for its specific task.
Right. That way, you're using both the CPU and GPU for what they're good at. CPU handles loading and pre-processing. GPU focuses on the heavy lifting, the model training.
Makes a lot of sense. It's all about dividing and conquering, each part working efficiently. What about data augmentation? We touched on it before. How does that fit into the data pipeline?
Data augmentation is super important for model generalization, helps prevent overfitting. You're creating variations of your training data on the fly, rotating images, flipping them, changing brightness. It helps the model see more examples, makes it more
In fact, a
robust.
more diverse training regimen, helping it recognize patterns in different contexts. But I imagine that adds computational overhead. Should we be doing those augmentations on the CPU or the GPU?
Good question. Doing it directly on the GPU can take up valuable resources that could be used for training. It's better to offload that to the CPU while the GPU is busy with the previous batch of data.
So it's like having a separate prep team working in the background, getting things ready while the chef focuses on cooking.
Precisely. That parallel processing keeps the GPU fed with data, maximizes its use.
Okay, so we've talked about the data pipeline. What about memory management? Deep learning models, especially those big language models, they can eat up a lot of memory.
Absolutely. Efficient memory management is critical. If you're not careful, you can run into memory problems, really slow down, or even halt the training process.
Yeah, those out-of-memory errors, no one wants to see those. What are some ways to manage memory effectively?
Well, a common mistake is holding on to data in the GPU memory for too long, like hoarding things you don't need. It just takes up space, makes it hard to find what you're actually looking for.
So decluttering, making sure we only keep the essential information easily accessible.
Exactly. Get rid of any data that's not needed as soon as possible. Frees up memory for other operations, helps prevent those memory errors.
Simple, but effective. But what if you're working with models that are so big they just don't fit in the GPU memory? What then?
Then we look at techniques like model parallelism. We can split the model across multiple GPUs. That lets you train those really big models that wouldn't fit on a single GPU.
So dividing the work, like a giant jigsaw puzzle. Each person works in a section, then you put it all together. But I imagine that can get complicated.
It can, you're right. You need to think about how to split the model, how the GPUs communicate. It takes a good understanding of the architecture, the hardware.
So it's like coordinating a team of movers, carrying a huge piece of furniture. Need a good plan and good communication.
Exactly. And then we have data parallelism, that's distributing the training data across the GPUs.
Oh, so to splitting the model, we split the data.
Right. With data parallelism, each GPU trains on a part of the data. Then the results are combined to update the model. It's simpler than model parallelism, often easier to implement.
Like having multiple cooks working on different parts of a meal speeds up the whole process.
Exactly. Data parallelism is really effective for speeding up training, especially when you have multiple GPUs to work with.
This is great stuff. Really interesting to see how we can use these different types of parallelism to break down those computational barriers and train those complex models.
And there's more. We can also optimize by choosing the right data types. Deep learning models use floating point numbers, and they come in different precisions. 32-bit, 16-bit, even lower, like bfloat 16.
Oh, like choosing the right level of detail for a photograph? Sometimes you need high resolution, other times a lower resolution works fine.
Precisely. Using high precision when you don't need it, it's wasteful, both in terms of memory and computation.
It's like using a sledgehammer to crack a nut. Way more force than necessary. But how do we know which precision to use without losing accuracy?
That's where experimentation and analysis come in. You want to find the lowest precision that still keeps the accuracy you need, saves memory and computation time.
Finding that sweet spot, balancing precision and efficiency.
Exactly. And there are techniques, like mixed precision training. You can use lower precision for some operations, but keep the overall accuracy.
Best of both worlds.
Right. And talking about getting the best out of our hardware, let's not forget those specialized features, like NVIDIA's Tensor Cores.
We've mentioned those before, but what are they again? How do they help with deep learning?
Tensor cores are these special units on the GPUs. specifically designed to speed up matrix multiplication. And that's a key operation in many deep learning algorithms.
So turbochargers for matrix multiplication.
You got it.
Ah.
But to really benefit from them, you need to use the right data types and operations. It's like having a high-performance car, but only driving in first gear.
Got to shift into high gear, unlock that full potential. What can we do to make sure our code is using them effectively?
One thing is to use data types that are supported by tensor cores, FP16 or BF16, for example. Those lower precision types are processed much faster.
So matching the data type to what the hardware can handle.
Right. And the structure of your code matters too. Make sure it's set up so tensor cores can be used well. For example, using matrix multiplications and convolutions with dimensions that align with how the tensor cores are designed.
It's not just the data type, it's how you organize the code to let the hardware shine. Any other low-level optimizations we should think about?
Well, vectorization is a common technique. You express operations in terms of vectors and matrices instead of individual elements. Lets the GPU process data in parallel much faster.
Like having a team of workers instead of just one. Gets the job done quicker.
Exactly. And then there's data alignment. It's about arranging data in memory in a way that's optimized for how the GPU accesses it.
Organizing your tools, everything in its place, easy to find. But don't modern compilers handle that automatically?
They do, to some extent. But sometimes you need to think about data alignment specifically, like when you're working with your own custom data structures.
So another one of those details that can really make a difference when you're trying to get the most out of your setup.
Absolutely. And speaking of compilers, don't underestimate their optimization capabilities. Modern compilers are really smart. Often they can optimize your code better than you can by hand.
They're like code whisperers then, making things more efficient behind the scenes.
Exactly. Use the right compiler flags and you can unlock a whole bunch of optimizations.
Like a secret weapon for optimization. But with all these different techniques, it can be hard to know where to begin.
That's true. It's important to be strategic about optimization. Don't try to do everything at once. Find the biggest bottlenecks first. Focus your efforts there.
Prioritize, like triage.
Exactly. And remember, profiling is your friend. Analyze how your code is performing, find those areas that need attention, and focus on those for the biggest impact.
This has been really insightful. So many different code optimization techniques, from data pipelines to memory management using special hardware features and compiler optimizations. It's a lot to take in.
It is, but we've seen how even small changes can make big improvements. And it highlights how important it is to really understand the hardware, how it works, to optimize code effectively.
Absolutely. But we're not finished yet. In the last part of our deep dive, we'll be looking at model optimization. That's about going beyond the code itself, focusing on making the models themselves more efficient. Stay tuned for the grand finale. Welcome back for the final part of our deep dive. We've covered a lot about optimizing our code, but now we're switching gears. Time to explore model optimization.
Exactly. It's like, we've got this powerful engine and now we need to fine-tune it. Really get that peak performance. Model optimization, it's all about making our models smaller, faster, more efficient, but without losing accuracy.
That's the key, right? It's like taking a race car, stripping it down, get rid of any extra weight that might be slowing it down. So what kind of techniques are we talking about here?
Well, we'll be looking at quantization, pruning, and knowledge distillation. They all offer different ways to, compress and streamline those models, make them more practical for real-world use.
Okay, let's start with quantization. What is it and how does it work?
Think about how we compress images. We make the files smaller, but we don't want to lose too much detail. Quantization's kind of similar. We're representing the model's parameters, but using lower precision data types.
So instead of those big 32-bit floating point numbers, we can use smaller ones, 8-bit integers, something like that.
Right, like packing your suitcase more efficiently. And you might think using lower precision won't that hurt accuracy? But modern quantization techniques are pretty advanced. They minimize that loss while making the models smaller and faster.
That's pretty impressive. So besides just making models smaller, what are the other benefits?
Smaller models mean faster inference. They use less memory. You can even run them on devices with less power, like smartphones or embedded systems.
So we're bringing AI to more places, more devices, it's more accessible, practical for all sorts of uses.
Exactly. Quantization is a big part of making AI work on those edge devices.
This is great stuff. Shrinking those models without sacrificing performance. What about pruning? What's the idea there?
Imagine a tree, right? Lots of branches. Some are dead, not doing anything useful. Pruning, it's like removing those branches, makes the tree healthier, more efficient. Model pruning's similar. We find and remove connections in the model that aren't really contributing to the overall performance.
Sort of like gardeners, trimming away the excess.
Exactly. And just like a gardener, we need to know what to cut. There are different techniques. Some look at the weights of connections, others see how much they contribute to the model's errors. The goal is to remove those connections safely without hurting accuracy too much.
It's like detective work, finding those connections that aren't doing their job.
Love that analogy. And the results can be amazing. You can often remove a big chunk of the model's connections without a noticeable drop in accuracy. Smaller models, faster inference, less computation.
Decluttering, making things more efficient. And it's not just about size, right? Pruning can also help the model generalize better.
Yeah, absolutely. By removing those less important connections, you actually help prevent overfitting. So the model's less likely to just memorize the training data. It performs better on new, unseen data.
Fascinating. Like simplifying an explanation, making it easier to understand and apply in different situations.
Yeah.
Okay, we've got quantization, we've got pruning. What about knowledge distillation?
Think of a master craftsman teaching an apprentice. Knowledge distillation's like that. You've got a bigger, more complex teacher model, and you're training a smaller student model to imitate it.
AI mentorship program, those smaller models learning from the experts.
Right. You train the student model not just on the data, but also on the predictions made by the teacher model. It's learning from the data and from the teacher's understanding of the data.
Wow. So it's like watching a master at work, absorbing their knowledge.
Exactly. And it works really well. You get smaller, faster models with accuracy close to the bigger, more complex ones.
It's like distilling knowledge into a more concentrated form, easier to handle.
Perfect way to put it. Knowledge distillation, it's all about that transfer of knowledge, making AI models more efficient without losing intelligence.
This has been incredible. We've learned about all these ways to optimize models: quantization, pruning, knowledge distillation, each with its own approach to making our AI models smaller, faster, better.
And these techniques are essential for getting AI out of the lab and into the real world. Running on devices with limited resources, making AI more practical for all kinds of tasks.
It's like we've made this powerful technology more portable, more adaptable, and ultimately more impactful.
Definitely. And this is just the start. As AI keeps advancing, we'll see even more amazing optimization techniques, pushing those boundaries even further.
It's a really exciting time to be working in this field.
Sure.
Well, as we wrap up our deep dive into multi-GPU and multi-node training, I want to leave you with a sense of, I don't know, maybe empowerment. These techniques, they might seem complex, but anyone can learn them, experiment with them. The tools are out there, the possibilities are endless.
Couldn't agree more. And the journey doesn't end here. Keep learning, keep experimenting, keep pushing those limits.
Thank you for joining us on this incredible deep dive. We hope you've gained some valuable knowledge and a new appreciation for the power of optimization. Until next time, happy training.